The universe may have crowned the wrong black hole, but the real mistake is not choosing Ton 618 instead of Phoenix A. It is pretending that the numbers attached to them mean the same thing. Ton 618 is often listed at 66 billion times the mass of the Sun. The black hole associated online with Phoenix A is often listed at 100 billion. Place those values beside each other and the result looks obvious. Phoenix wins. But one number comes from the spectrum of an exceptionally distant quasar. The other famous number comes from a model that suggested the Phoenix cluster's central black hole might be of order 100 billion solar masses. It was not a direct dynamical measurement, and NASA's current material describes the Phoenix black hole as roughly 10 billion suns. So before we crown anything, we need to answer a more important question. How do astronomers weigh an object that produces no light of its own? Before we go deeper, subscribe to Endless Astra for more real cosmic stories built on science, mystery, and the true scale of the universe. Ton 618 is a quasar whose light has traveled for more than 10 billion years to reach us. The black hole itself is invisible. What we detect is matter falling toward it. Gas spirals into an accretion disk, becomes extraordinarily hot, and releases enough radiation to overwhelm the surrounding galaxy. That light is not only bright, it carries a record of motion. Astronomers split the quasar's light into a spectrum and study broad emission lines created by gas moving near the central black hole. The broader the line, the greater the range of velocities in the emitting gas. If astronomers can estimate how far that gas lies from the black hole, they can combine distance and speed to infer the mass required to keep it moving. This is a single epoch virial mass estimate. It is one of astronomy's most useful tools for distant active galaxies. It is also built from assumptions. The broadline region cannot be resolved as a clean orbit around TON 618. Its size is inferred from the quasar's luminosity. Its velocity is inferred from the width of an emission line. A calibration factor then attempts to represent the geometry and orientation of the gas. But the gas may form a flattened structure. Part of its motion may come from winds rather than gravity alone. Radiation pressure may matter. A face-on system and an edge-on system may produce different line widths. And relations calibrated on more ordinary quasars may become less secure when applied to an object as extreme as TON 618. This is why a mass estimate can change without either group behaving irrationally. The famous value near 66 billion solar masses came from broad-line spectroscopy and remains the figure used in current NASA material. Another published analysis using a different emission line treatment produced a value near 40.7 billion solar masses. Those are not two readings from a cosmic weighing scale. They are model-dependent estimates extracted from light. Even the lower value leaves Ton 618 among the most massive black holes known. For a non-rotating black hole in the 40 to 66 billion solar mass range, light would need roughly 9 to 15 days merely to cross the event horizon diameter. But when the question is which object holds the record, a difference of more than 20 billion suns is not a minor detail. Then the Phoenix cluster entered the comparison. The name Phoenix A properly refers to the enormous central galaxy of the Phoenix cluster, about 5.8 billion light-years away. Online, the same name is often applied to the black hole inside it. The environment is extreme. The cluster contains vast amounts of X-ray emitting gas. Cooler material flows through its central region. Stars form at a remarkable rate. Jets and radiation from the active nucleus interact with gas on enormous scales. A giant black hole clearly sits at the center. The difficult question is how giant. In 2012, Chandra material described it as about 20 billion solar masses. In 2019, Chandra used 5.8 billion. NASA's 2025 Webb report described a roughly 10 billion solar mass black hole, and the associated research emphasized that its mass is still only weakly constrained. So why does 100 billion appear so often? There is a scientific source behind the possibility. A 2016 study proposed a new model for identifying the most massive black holes in brightest cluster galaxies. By connecting black hole growth, feedback power, and changes in the central stellar density, the authors suggested that the Phoenix cluster's black hole might have a mass of order 100 billion suns. That is a serious hypothesis. It is not the same as resolving stars or gas in orbit and measuring the central mass dynamically. It is a model-based extrapolation applied to one of the most exceptional galaxies known. That distinction disappeared as the number traveled.
A candidate became a fact. A possible order of magnitude became a precise mass. Then, comparison graphics placed a 100 billion solar mass Phoenix black hole beside a 66 billion solar mass Ton 618. The circles looked exact. The ranking looked settled. But the visual certainty was created by the artwork, not by the measurements. A black hole has no visible solid surface. The dark circle used in a size comparison is calculated from an assumed mass. For a non-rotating black hole, double the mass and the Schwarzschild radius doubles. Change the mass estimate, and the entire visual object changes with it. At 10 billion solar masses, the Phoenix cluster's black hole would be far smaller than ton 618 under either major ton estimate. At 20 billion, it would still be smaller. Phoenix overtakes ton 618 only when the model-based value near 100 billion is treated as established. That does not prove the Phoenix black hole cannot be that massive. It means the current evidence does not support presenting the ranking as settled. And the comparison becomes even less certain when we ask for the largest black hole in the universe. Astronomers can rank only the objects they have discovered and measured well enough to estimate. Active black holes advertise their presence because infalling matter shines. Dormant black holes may remain almost invisible inside distant galaxies. The largest object may therefore be one of the quietest. A black hole does not reveal itself. Its surroundings reveal it. When the surroundings stop glowing, the monster can disappear from our surveys. There may be black holes approaching or exceeding 100 billion solar masses. Models allow scientists to investigate that regime, and some exceptional central galaxies are plausible places to search. But physical possibility is not identification. Showing that a black hole could reach 100 billion suns does not demonstrate that a particular galaxy contains one. So which is larger, ton 618 or the Phoenix cluster's central black hole? Based on the most widely supported, published, and official values, ton 618 remains the stronger candidate. NASA currently presents ton 618 above 60 billion solar masses, while its current Phoenix material uses roughly 10 billion. Even the lower published estimate near 40.7 billion for ton 618 exceeds the 5.8 to 20 billion range that has appeared in Chandra material for Phoenix. But that answer still needs an asterisk. Ton 618's mass is inferred through virial methods, not measured from individually resolved orbits. Phoenix's mass remains weakly constrained, and its extreme environment makes ordinary galaxy scaling relations difficult to trust. Future observations could move either estimate. The deeper lesson is not that astronomy failed. It is that extreme measurements are provisional. Astronomers infer black hole masses from spectra, timing, motion, luminosity, gas temperature, lensing, and gravitational influence. Each method carries its own assumptions and uncertainties. Scientific papers preserve those uncertainties. Popular rankings often remove them. A range becomes one number. A model becomes a measurement. A possible upper value becomes a record. Then, the universe appears cleaner than the evidence really is. Ton 618 may still be larger. The Phoenix black hole may eventually surprise us. Another known candidate may surpass both once its mass is measured more securely. Or the true record holder may be dormant, distant, and almost invisible. Until the measurements improve, there is no perfectly weighed champion. There are estimates, there are models, there are probability ranges, and there is a universe that refuses to fit neatly inside the circles we draw for it. Drop a comment. Which surprised you more? The uncertainty around ton 618, or the fact that Phoenix's famous 100 billion solar mass value is a model-based possibility rather than a settled measurement?